Hello, I am Andreas Zeller. I'm the author of the Debugging book, and I'm here to present you a new chapter. These chapters, as you see them here, and as they come with text and Python code, whatever, these actually all are so-called Jupyter Notebooks. If you go to Resources and then look at Edit as Notebook, what you're going to find in there is, this doesn't work anymore, too bad. What you're going to get is an environment where you see the same material as in the chapter, except that this is an interactive environment, which means that you can actually go and change things as you like. This is lots of fun, and this opens for lots of very interesting consequences. In particular, you can run all your experiments as you like. And for this, you have a couple of choices. You can either edit this right in your browser. You can try this out right now if you wish, and then you should be able to see this right away. But you can also go and download the code to your hard disk, to your computer. You can also download the notebook on your computer and then work with it by yourself. Oops, it has just downloaded the whole thing. And you can also download archives with all code that is there and all notebooks that are there. So there's a couple of opportunities for you. And but your main working environment should be the notebook. And this is what such a new notebook looks like. I have now opened the first chapter in my Jupyter Notebook. And here you see the very same text as I already have it here. So this is Introduction to Debugging, and here's an introduction text. And this is the same material, except that in my Jupyter Notebook, I can actually edit things. So I can go and edit this text. Well, that's interesting if I want to write a book. But I can also edit these code sections. All I need to do is I can click on these, and then I can edit things as I like. Well, that's a very simple thing. And then I can even execute them, and I can try them out as I like. And this is also the same environment that you will be able to use for your project, which means that you can actually experiment with all the code and try out the individual examples, try out what's happening in there, find out what the individual parts are doing. That's one thing. And you can, and you can also use the very same environment to actually build your projects and to build your own extensions to the material that is around. So a couple of things of questions. So do we have new questions, Johannes, or shall I just continue?
Yeah, there was one more question, whether the criteria of how we judge the submissions will be made clear in the project requirements, but this is the last question there was.
Yes.
I mean, again, we will make sure that you know what you have to do, and we will judge the projects according to what we want you to do. So it should be clear how we judge the submissions. Yeah.
Okay. So for the rest of today's lecture, I'm going to give you a short teaser on the material that you are supposed to process for next week. We're going to have a single example, and this is one example that is going to follow us for quite some time, because it's an example where one can illustrate a number of debugging techniques, manual debugging as well as automated techniques. And that's assuming that you now have the chapter actually opened up in your Jupyter environment. As I said, you can be in here and then you go to Resources and Edit as Notebook, and then it will automatically open this wonderful binder environment, and then it will launch the server automatically for you. This normally takes about 1 minute, and then you can edit things right in your browser. I'm going to use Jupyter Notebooks as I already have it open on my machine in order to save a bit of time. What we're going to do in our example function is, the idea is that we are going to remove HTML markup. HTML. I assume that most of you already have seen HTML source code at some point, or at least know the basics of it. It's not very complicated. It's not very complicated. This is a text that comes in, so this is a bit of text that comes in HTML. And you have this HTML markup, which comes with these special markup tags, for instance, in order to make sure that some text is emphasized, as in here. And then this will, a text like this in HTML, will be rendered like this in your browser. So this is emphasized, and you can see that emphasized over here is actually shown, well, in an emphasized way. Interestingly enough, you can actually do your own HTML experiments, because you can actually look up the source code of this whole thingy, and you can actually enter your own tags to this just to see how they look like. So if you want to experiment with HTML, this is what, say, the strong element does, and this is just regular emphasis. So we go back again. So normally we're not going to edit these text parts. This is this is already a given. But what I want to build today is a function that actually goes and takes away these HTML tags. That is, it takes an HTML input, such as this one, and then it converts this into regular text without any particular markup or anything. Maybe useful if you want to pipe an HTML page into a text editor. And our idea is to write a simple Python function, which does precisely that. So Python. Python. Python is a language that is, well, that is that is a bit special. If you have been programming in Java or a language like C before, the first thing you will notice is there are no types. That Python is a dynamically typed language. That is, a function like this, like remove HTML markup, which takes an argument s. Well, you can pass in any s that you like, although the name s may suggest a string, which it is. There is no static type checking. Types are being checked dynamically, meaning that if something goes wrong, you will notice at runtime. We also have a couple of types, but you have a couple of types in here. You have Boolean values. So I'm having a Boolean variable, which is named tag, and I'm having a string variable, which is named out. And if you just find that this is underlined here, that's because we don't use these yet. Another interesting thing about Python is that there are no braces. So in other languages, you may have braces like these, and well, maybe something like that at the end. And oops, all of a sudden, this looks like C or C++. There is nothing like that in Python either. Instead, Python structures your code by indentation, meaning that any code that is indented in here under this definition keyword actually belongs to the definition of a function. And if something is outdented, so if I write something like x equals 442, then this is outdented. This is no longer indented as in here. This is an assignment to a global variable at this point, whereas if I indent it, then this becomes part of the function definition. So, but still, this is a function, and you have seen functions. There's nothing special about a function in here. So I'm going to build this function which removes this HTML markup. And the first thing we're going to do is I'm going to build a loop. So this is a loop, and this iterates over all elements in S, which is a string, and the iteration variable is C, that is a character that is for every character in that string. JavaScript has a similar thing. There you also can iterate over elements of a list. I think in C++ it's possible to iterate over lists. Otherwise, if you program in Java, does Java have iterations over lists? That's an interesting. Yeah, in Java, I think in Java it's named for each or something. That's a common thing. So now I'm having something. I'm going through all of this. What I want to do is I want to go through over all the characters in that string. And now I want to check whether something is maybe the beginning of a markup, something like that. If C equals an opening angle, and you see this is all very common as well. This is just the same keywords as in other languages. So you have if, you have equals as in C, and here I have a comparison against. This looks like a character. In fact, it's not. I can also write it like this. Then Python has no specific notations for characters. Everything is a string, and strings can be enclosed both in double and single quotes. Sometimes it's useful. This can be useful if I want to check, for instance, if something is a quote, I can write it like this, or I can also check for a single quote, and I can enclose the string in double quotes instead. An interesting thing happens if a string is enclosed. If a string has both single and double quotes, then well, I have to go through extra tricks. But we are simply going to go and check for a single character here. In all generality, in this book, I'm using single quotes when something is when a string is internal, and I'm using double quotes if a string actually is end user facing, and this string is not end user facing, so I'm using single quotes. So what we're doing here is if we are finding an open angle, then we set the variable tag to true. Otherwise, if we find a closing angle, here we go, wonderful, then we set tag to false again. And now the fun part comes. Oops, false. Thank you very much. Where is auto-completion if you need it? And the interesting thing is that otherwise I'm going to add the out is out plus C. I'm going to add the character to our out variable, but only if tag is not set. This means that if I encounter an opening angle up here, I'm going to set tag, and then everything will be ignored until I find the end of the angle, and then tag is false, and then characters will be added again. So this is a very simple way of writing out. I can also use a typical C-like compression here. I can write out plus equals C, and then this simply means that that character string C will be appended to out. So this is it, but I can also do this in a very simple way, and then it will be super readable. There we go. And then in the end, once I've done that, I do return out. And I think I'm done at this point. Do we still have anything that is, why is this thing underlined? I have no idea. Interesting question. What happens here? Invalid syntax. What did it? Oh, yes. Oh, sorry about that. That's actually something where somebody in the live audience can raise their hands and say, why Professor Zoller, are you putting two ifs in here? But fortunately, I have my own electronic stuff here, which helps me out with that. So this is now my function remove HTML markup. And now comes the fun part. In a Jupyter Notebook, I can press Shift and return to automatically execute whatever is in here, and then it will be executed right away. If I do any mistake in here in this code, for instance, by having another if in here, there we go, boom, then I'm going to get syntax errors, invalid syntax, and I can fix things right away. So here we go. Apparently our function is syntactically correct, which actually also means that now I do have this function defined, and I can actually now invoke it, and I can see what happens if I invoke it with, say, a string like foo, and I get the result right away. So I'm typing in. This is a bit like a read eval print command line loop. And I can enter commands as I will, except that I always see what I have entered before, and I also see the results of things right away, and they stay within my document. I can save the whole thing, and everything stays in here. So this is the remove HTML markup of foo, and that's not very exciting because this string actually does not contain any HTML markup. And I can now add some HTML markup. So let's make this emphasized whatsoever. Boom. Here we go. And this also works. Wonderful. Yeah, cool. Ha. I am the coolest person on earth because I just managed to write a small little Python program. So as you see, there's really nothing, there's not too much exciting about there. You have if, you have else ifs, you have comparisons, you have booleans, you have string operations. Yes, and behold, numerical operations like, say, additions or floating point numbers whatsoever. They all very much behave as you know them already from other languages. But I can now also go and I can also go and say I want to check whether this is correct or not. And then I say, okay, I'm having this function in here, and it should return true. Or and then I can go, if should this by any chance not return foo, then I'm going to, oh, what can I do? Can I raise an error? Can I raise an error? That's a good question. Yeah, possibly. Well, I don't know yet. I have to make a mistake in here first. That raise error or name error is not defined. Too bad. Well, but actually that's for a good reason, because this remove HTML markup of thingies. Oops, here we go. I'm going to copy this all here. I'm going to add this down here. Now no longer returns foo because it adds an X character all the way. So you can easily simulate things as we like. Okay, good. So we have a function for removing HTML markup, and we're done. So great. This was your exercise for the day. Thank you very much. I'm sorry, we're not there yet, because as everybody knows who's ever been doing some HTML, who's ever worked with HTML, HTML tags do not simply consist out of angle brackets and identifiers like these, but there are also more complex. More complex tags. In particular, a tag can take arbitrary attributes. For instance, if I want to write a link to foo.com, that would be interesting. I have no idea what's behind foo.com. So let's make this debuggingbook.org before we infringe somebody's copyright. Then this also works. We're still good. Everything is fine. That's all perfect. Wonderful. The problem is, however, that these things here that actually come as arguments, they can also take less than and greater signs. So what happens if I do this, for instance? Exciting question. So I think this is going to work just fine. Is it? Yes, it works just fine. Everything is automatically removed. But here comes the fun part. What do I do here? If I have such a quoted character in my HTML tag, note the HTML tag goes from here to here. Okay, so this character here is actually not part of the HTML tag. However, our remove HTML function here doesn't know this. So what happens is that the single quote here, which we have here at the very end, is all of a sudden included, because our remove HTML markup function has no idea about quotes. Okay, so we're stuck. Our function doesn't work as it should, and this is a bad thing. So now we have to go and actually fix it. Well, there's a couple of ways to fix it. A very simple way to fix this is, well, we can just fix what we see, and we can come up with a very simple fix to thingies. So we can say if s equals this string, return foo, boom, fixed, huh? See, that's a very simple way to fix things. This is of course not a preferred way to fix things, but this is actually a technique which some programmers apparently use to patch their code such that it passes all the tests. And yes, this is going to work just beautifully. There's even examples of banking code where, well, not so smart programmers have managed to work around some issues and whatever. Yep, this is a typical problem of a fix that only fixes the symptom and not the cause. That's one problem, but doesn't really work well. Another technique which you can do is so-called printf debugging. Printf debugging means we are going to insert lots and lots of print statements into our function. So, and there's also a print statement in Python, and it's super popular. It can take anything. So here already comes the automatic guide for what you can do during printing. So I can say I want to print S, for instance. If I do print S, then the string is automatically going to be printed out to my console. And print takes everything. This is called printf debugging because in C there's a function called printf which has the same function. So it takes a format on top of it, But you can now go and just say, okay, I'm going to look into whatever happens here. What is my S? What is my C? And I can look out through the individual characters, yes, and how they're being added. And I can add another one and another one. So let's do this here so I can print out just because I can. Oops, so bops. And then you're going to clutter your output with plenty of extra statements. Yes, you can do that and figure out what's going on, but we already know what's going on. Well, our remove HTML markup function has actually no provision for quotes whatsoever. Okay, and so what are we going to do with this? What are we going to do with this in this chapter? So what we're going to do here is we're going to go and take this array function. Here it is again. Let's make this a bit bigger for you so that you actually can see things. Here we go. By the way, this hash character here is the beginning of a comment. This is like shell comments, for instance. Here we go for the standard stuff. Here we go for the interaction stuff. That's what we have just seen. And here comes a typical example of how things work badly. And what we will be going through in this chapter is, first, we're going to introduce a somewhat more abstract notation for what's going on in our code. Namely, we're going to look into a finite state model that actually shows what is happening in here. So we start with things, and then we have a character that is not an angle, we add it, and then we are in the status of not tag, we go into the status of tag. And what we do not have here is anything that actually checks for these things. We can now add another state, which is quoting things or not quoting things. And then we can make sure that if we are in a quoting state, then tag characters will actually be ignored until we come to the end of the quoting. And then we end up with this extended remove HTML markup, which accepts these smaller signs and greater signs only if quote is not set, and quote is set whenever, or actually quote is toggled whenever we see one of these greater or one of these double or single quotes. And now this works, but there's other things which do not work, and we now continue with various iterations through the entire program. We also build up a bit of theory, how the failures come to be from defects to failure. And this is then how we can then systematically process the bug and systematically use a method called the scientific method to systematically find out what's going on. The scientific method, I'm going to spend another couple of minutes on that because this is a very important thing to know whenever you're manually debugging, and I really don't want you to miss this thing. The thing is, this is a very simple diagram of the scientific method. Scientific method is actually a method by which you can come to scientific findings very systematically, not only in debugging, but actually anywhere in nature. You start with some observation in nature. Why does this apple fall down, for instance? And then you wonder, why is that? And you come up with something that is called a hypothesis. You come up with a possible cause for what you just observed. In debugging, this can be a problem report. This can be code, this can be runs, or this can be more runs. All of these influence your hypothesis. And from this hypothesis, you build what is called a prediction. That is, you say, okay, if my hypothesis holds, then the following must happen too. And then you have made a prediction. And this prediction is then something that you verify in an experiment. And from this experiment, you get then more observations that tell you whether your hypothesis is supported, and then you refine it, or whether your hypothesis is rejected, and then you come up with another alternative. So what could possibly be wrong with our function right now? Oh, it doesn't handle quotes. So I'm going to make a prediction. We need to handle quotes in a particular way. Then I make an experiment by handling quotes in a correct way. I make an observation. Quotes are now handled correctly. So let me check whether this actually holds further. Or I didn't implement this correctly. Then I need to seek an alternative. Okay. And this allows you to treat bugs as if they were natural phenomena, and you can systematically narrow down one part of the input after the other. And we also have a couple of quizzes in here, which allow you to check whether things are correct or not. So let me just try out. So, oh, this was by pure chance. How could I possibly do that? Okay, good. Just ignore what I just typed, and I'm not going to tell you what's the right answer. And here we go through a number of extra steps in order to further refine our function. And in the very, very end, after going through all the quizzes and everything that we have seen, we actually come up with a version of our function that actually works. Okay, all of this coming up with a number of experiments and going through the individual steps is actually something that is similar to the game of Mastermind. Mastermind is a game for two persons. You have one person who's sitting here at the end and who's coming up with a secret color combination. And you have another person sitting in front who's trying to guess that combination. And for every input, in here, the player whose pins are hidden provides some feedback on the number of pins which have the correct color, and possibly also the correct position with these white pins and red pins. And from this feedback, our mastermind, that is the player who needs to figure out the secret combination, comes up with more and more attempts, comes up with more and more experiments and more hypotheses on where the individual pins could be, until all the pins at the very end and until all the pins are in their correct position. And of course, every new experiment must be consistent with all the earlier observations. If you look at this, there's also something else which is important for debugging, namely that you want to make your individual hypotheses and your results explicit, such that you can look them up. Such that you can find out what you have tried out before and what the result was. This is actually also where Jupyter Notebooks come in very handy, because they actually allow you to track everything that you've done before. And by making these things explicit, this makes you a better debugger, because you don't have to keep everything in memory. You can always look down on what your previous results were. Making things explicit also gets us to our second big technique in the manual debugging, and this is called rubber ducking. If you've never heard of rubber ducking, that's a technique which is fairly simple. If you have a bug and you have a problem for which you don't have the cause, you should go and try verbalizing it. That is, explaining it to someone. And this someone can even be an inanimate object, such as a rubber duck. If you explain a problem to a person or even to an object, you will be forced to rethink your hypotheses and try them and think about them again, and making them explicit, making your process of reasoning explicit. And this helps a lot for debugging. When I was a student, there frequently were other students coming to me and asking me, Andreas, I'm having this this also happened to me as a student tutor and later on. Andreas, I'm having this particular problem over here. I am feeding this gobbledygook into this bubble notch, but I'm using bubble notch version 2.0. But whenever I'm feeding this bubble notch in an invariant state, and it gets into an invariant state because I've checked this, and then this invariant state. Actually, now that I think about it, I have not checked whether this is an invariant state. Let me first, Andreas, let me first check whether this actually is an invariant state, because it may actually not be one. Yes, it actually may not be one. That's true. Thank you very much, Andreas. And I was just there, and I didn't understand a thing, and I was just there, nodding and smiling. I was taking the role of the rubber duck here, and I knew that about 2/3 to 3/4 of all cases, people would come up with a solution by themselves, simply telling things to me. And but there were plenty of people coming to me, and every time, simply by sitting there and nodding and not understanding a single thing, I would be able to fix their bugs. And this is how I became a professor where debugging would be one of the specialities. Well, I'm your rubber duck. Of course, it's not very efficient to have a full-fledged professional just listening to your whatever debugging stories. So actually, it's a very good practice to first take a rubber duck or whatever object and telling this to the rubber duck first. I happen to have a Coke bottle here on my desk, and I could actually go and explain to my Coke bottle why my computer keeps on crashing. This could be very interesting. Maybe the bottle is going to help. Doesn't matter as long as I explain all the steps I've taken. Okay, oops, and we also have a short section on the history of debugging here, and also just for the fun of it, there's the word bug, which we commonly assume is something that creeps into our programs and then causes our programs to fail. This is a very nice yet misleading picture, because it is not bugs that cause our programs to fail, or, well, it is not bugs that come from the outside. We have created these bugs. It's still us programmers who are responsible. But here's a picture that should actually be in every single book, on every single course on debugging. This is from Grace Hopper on the Harvard Mark II machine in 1947. This is the first actual case of a bug being found in a computer. This was a moth that was stuck in a relay and therefore caused a computer malfunction. And you can actually see here, this is the first actual case of a bug being found. This is how the engineers at the time logged it in their notebooks. Which actually brings us to the point that the term bug is much, much older than computing by itself. Already Edison talked about bugs. And if you look further earlier, you will even find bugs in the sense of a nightmare, or something that is not under your control and threatens you. You will even find references to bugs in Shakespeare's work. This is how old bugs are, and this is how old debugging is. Okay, with that, I think I have gotten you some. I've gotten you some material to read for the next week. This is mostly just for you to getting acquainted with the field, or say, and mostly also with its terms, with manual debugging. In the week after, that is next week, we will go into actual programming, namely into tracing executions. And this is where we will then actually build our first debugging infrastructure, which now goes through individual parts of the function now with tracers and logging functions. And that actually these are actually a number of techniques that allow you to have the program to log the execution and show specific events and everything. But this is something we're only going to see in the week after.